In this video, I'm going to show you how to import your CAD from Onshape, add joints and motors to create a physics-based simulation, and train the robot to bounce a ball using reinforcement learning. You can find the complete CAD for this demonstration available publicly on Onshape. We'll start by importing the CAD directly from Onshape into ProtoTwin. You can search through your documents and select the main assembly to import. This process may take a few seconds. The next step is to add physics to each link of the robotic arm. We'll create a revolute joint and configure the axis and anchor properties of the joint using feature selection. To test our work, let's switch over to Navigate mode and run the simulation. This allows us to interact with the physics. Okay, let's now add physics to the second link. The process is the same as before. Set the constraint type to revolute and configure the axis and anchor properties by selecting appropriate features from the CAD. However, this time, we'll set the base property of the revolute joint to the first link. This creates a joint between the first link and second link. When we run the simulation, we can see that the two links are indeed now correctly constrained by a joint. Let's now attach a motor to each joint. We'll use a position controller so that we can drive the joints to whatever angle we want. You can also change the motion parameters, such as the maximum velocity and acceleration. If we run the model, we can set the target position for the motor and watch the motor drive the joint. To finish up the setup, all you need to do is repeat these steps for the 4 remaining joints. For reinforcement learning, we need to drive the joints externally from a Python script. Each component in ProtoTwin can expose some I/O. Here you can see the I/O for the motor component. The inputs are on the left in green, and the outputs are on the right in red. Switching over to the I/O browser, we can see the full list of I/O in the Signals tab. Our Python script will read outputs, such as the current position of the ball, and write inputs, such as the target position for each motor. If we run the simulation, we can see that the model setup is now complete. I've created a very simple Python script, which contains everything needed to train the robot to bounce the ball. At the top are the addresses for all the I/O that we'll be reading and writing. These variables are copied straight out of the I/O browser in ProtoTwin. Next, we define our gymnasium environment. This consists of a few simple functions for computing the reward and penalty terms. We reward the agent based on how close the height of the ball is to a desired target height. We penalize the agent for moving the bat far away from the initial position. We also penalize the agent based on the torque produced by the motors. These penalty terms help to ensure that the agent positions and moves the robot more naturally. We combine all 3 terms into a single reward value, which is used to score how well the agent is performing at the task. A terminal function is used to detect when the agent needs to be reset. We do this when the ball has fallen below a certain height, or when either the ball or bat have moved outside of some bounds. Lastly, the main function instantiates our environments and starts the training process. The complete source code is available in a GitHub repository. Here, you'll also find a number of other examples, including the canonical cart pole swing-up environment, a variant of the cart pole that includes domain randomization, a bipedal locomotion environment, a quadruped handstand environment, the robotic ping pong environment that we're training here, and a quadrotor drone environment. We'll be adding additional examples over time. Okay, I've kicked off the training by running the script. The network is initialized with random weights, resulting in random actions. The agents perform poorly, and they receive a low reward. Just 8 minutes later, the agents are just beginning to be able to bounce the ball multiple times. The reward has increased by a factor of 100, and the average episode length is about 3 seconds. Fast forward another 12 minutes, and we see that the agents have learned to bounce the ball for nearly the full duration of the episode length. Further training at this point is likely to provide only marginal improvement. You can use TensorBoard to help monitor the training progress. The first plot shows the mean episode length, which is how long each agent is able to bounce the ball for on average. The second plot shows the mean episode reward. We can see that the plots are highly correlated. This is expected, since bouncing the ball for longer should result in a greater reward. And here's the end result. You can use the built-in inference component to run the trained model inside ProtoTwin. I hope this video demonstrated how quick and simple it is to train custom agents with reinforcement learning using ProtoTwin. Thanks for watching.